I am Geetha, Assistant Professor, Department of Mathematics. Now we are going to see case study on Bayes' theorem. Problem statement 1. In a bolt factory, machines A, B and C manufacture respectively 25%, 35% and 40% of total. Of their output, 5%, 4% and 2% are defective bolts. A bolt is drawn from the total output and is found to be defective. What is the probability that it was manufactured by the machine B? Here, let us consider a bolt factory. It has machines A, B and C. A produces 25%, B produces 35% and C produces 40% of bolt. Of their output, 5% are defective from A, 4% are defective from B and 2% are defective from C. A bolt is drawn from the total output and is found to be defective. Now we are going to check what is the probability that it was manufactured by the machine B. By solving the above problem, we are going to use Bayes' theorem. Bayes' theorem, named after 18th century British mathematician Thomas Bayes, is a mathematical formula for determining conditional probability. Bayes' theorem uses the available information and incorporates conditional probabilities into conclusions. In probability and statistics, Bayes' theorem describes the probability of an event based on prior knowledge of condition that might be related to the event. Prerequisites for Bayes' theorem: probability rules, trial or event, exhaustive events, mutually exclusive events, conditional probability and total probability. Now, probability. Probability means uncertainty about happenings. Probability is a numerical value of likelihood or chance of something happenings. Generally, we discuss probability as a fraction, decimal, or a percent. Next, probability rules. Probability of an impossible event is 0. For example, we can live without water. It is impossible event. In this case, probability of an impossible event is 0. Probability of a sure event is 1. For example, sun rises in the east. We can't change this attitude. So, probability of a sure event is 1. Next, probability values always lies between 0 to 1. For example, Arun may gets that job. In this case, Arun may or may not gets that job. So, probability values here lies between 0 to 1. Next, the sum of probabilities of all possible outcomes of an event is 1. Next, trial or event. The performance of a random experiment is called a trial and the outcome is called an event. Example, throwing of a coin is a trial and getting head or tail is an event. Next, exhaustive events. Events are said to be exhaustive when they include all possibilities. For example, in tossing a coin, either the head or tail turns up. There is no other possibility and therefore these are exhaustive. Next, mutually exclusive event. Events are mutually exclusive if they have no outcome is in common. This is the same as saying their intersection is empty. The symbol for the empty set is phi. that is nothing but the set with no elementary outcomes. For example, in throw of a single dice, the events of getting 1, 2, 3, 4, 5, 6 are mutually exclusive. Next, conditional probability. The conditional probability of an event given another is the probability of the event given that other event has occurred. If P of B greater than 0, P of A given B is equal to P of A intersect A and B divided by P of B. Here the event B is already occurred. Then only A can occur. For example, if you want to join any degree course means you should pass in +2 level. So here B is nothing but you should pass in +2. Then only you can join the degree course. With more formal notation, P of A/B is equal to P of A intersection B divided by P of B. If P of B greater than 0. The vertical bar represents the conditioning and is read given. So, P of A/B is read the probability of A given B. Next, total probability. The law of total probability. If B1, B2, etc. form a partition, then P of A is equal to summation I P of Bi into P of A given Bi. The law of total probability says that the unconditional P of A is a weighted average of the conditional probabilities P of A given Bi weighted by the probabilities of the condition P of Bi. Next, Bayes' theorem. Let B1, B2, etc. Bn the exhaustive and mutually exclusive events, random experiments, and capital A Bn event related to that B. Then P of Bi given A is equal to P of Bi into P of A given Bi divided by summation I is equal to 1 to n P of Bi into P of A given Bi. Next, proof of Bayes' theorem. P of A intersection B is equal to P of Bi into P of A given Bi. Here we are using the conditional probability. That is, P of Bi intersection A can be written as P of A into P of Bi given A, or which is equal to P of Bi into P of A given Bi. Therefore, P of Bi given A is equal to P of Bi intersection A divided by P of A. Now, P of Bi intersection A can be written as P of Bi into P of A given Bi. So, the above will be P of Bi into P of A given Bi divided by summation I is equal to 1 to n P of Bi into P of A given Bi. Instead of P of A, we write summation I is equal to 1 to n P of Bi into P of A given Bi. Here we are using the total probability concept. So, P of Bi given A is equal to P of Bi into P of A given Bi divided by summation I is equal to 1 to n P of Bi into P of A given Bi. Next, solution to the problem 1. Let E1, E2, E3 be the events that the bolts are manufactured by machines A, B, C respectively. Given in a bolt factory, machine A manufacture 25% of the total output. Therefore, probability of E1 is equal to 25%. That is equal to 25 by 100, which is equal to 0.25. Also, in a bolt factory, machine B manufacture 35% of the total output. Therefore, P of E2 is equal to 35%, which is equal to 35 divided by 100, which is equal to 0.35. Given in a bolt factory, machine C manufacture 35% of the total output. Therefore, P of E3 is equal to 40%, which is equal to 40 divided by 100, which is equal to 0.40. Let capital D be the event of drawing defective bolt. Therefore, probability of drawing defective bolt from machine A is equal to P of D given E1, which is equal to 5 by 100, that is equal to 0.05. Next, probability of drawing defective bolt from machine B, that is equal to P of D given E2, which is equal to 4 by 100, equal to 0.04. Next, probability of drawing defective bolt from machine C is equal to P of D given E3, that is equal to 2 by 100, which is equal to 0.02. Next, to find the probability that the defective bolt selected as random is manufactured from the machine B. That is, we have to find P of E2 given D. Here we are going to use Bayes theorem. So, P of E2 given D is equal to P of E2 into P of D given E2 whole divided by P of E1 into P of D given E1 plus P of E2 into P of D given E2 plus P of E3 into P of D given E3, which is equal to P of E2 value is equal to 0.35, P of D given E2 is equal to 0.04, and P of E1 equal to 0.25, D given E1 equal to 0.05, and P of E2 equal to 0.35, P of D given E2 equal to 0.04, P of E3 equal to 0.04, and P of D given E3 is equal to 0.04. Substituting the values in the above equation, we get which value is equal to 0.014 divided by 0.0125 plus 0.014 plus 0.008, which is equal to 0.014 divided by 0.0345, which is equal to 0.406. Next, problem statement 2. A given lot of IC chips contain 2% defective chips. Each chip is tested before delivery. The tester itself is not totally reliable. Probability of tester says the chip is good when it is really good, 0.95. And the probability of tester says chip is defective when it is actually defective is 0.94. If a tested device is indicated to be defective, what is the probability that it is actually defective? Here we are having lot of IC chips. It has 2% of defective chips. Each chip is tested before delivery. They have given the probability of good chip is 0.95. Probability of defective chip is 0.94. If your tested device is indicated to be defective, now we are going to find what is the probability that it is actually defective. Solution to the problem 2. Let E1 be the event that the chip is actually defective, and let E2 be the events that chip is actually good. Let D be the event of tester saying good. Therefore, P of E1, that is nothing but probability of chip is actually defective, is equal to 2 by 100, which is equal to 0.02. Next, probability of event that the chip is actually good, which is equal to P of E2, that is nothing but 1 minus P of E1, which is equal to 98 by 100, which is equal to 0.98. Next, probability of tester says the chip is good when it is really good. P of D given E2 is equal to 0.95. P of tester says that the chip is good when it is really defective. P of D bar given E1 is equal to 0.94. Next, we have to find P of actually defective chip, that is equal to P of E1 given D bar. Here we are going to use Bayes theorem. P of E1 given D bar is equal to P of E1 into P of D bar given E1 whole divided by P of E1 into P of D bar given E1 plus P of E2 into P of D bar given E2, which is equal to 0.94 into 0.02 divided by 0.94 into 0.02 plus 0.05 into 0.98, which value is equal to 0.2772. Next, problem statement 3. A company has two plants to manufacture scooters. Plant 1 manufacture 80% of the scooter and the plant 2 the rest. At plant 1, 85 out of 100 scooters are related to higher quality, and in plant 2 only 65 out of 100 scooters are rated. A scooter is chosen at random. Find the probability that the scooter came from plant 2. Here they have given a company has two plants to manufacture scooters, plant 1 and plant 2. Plant 1 manufacture 80% of scooters and plant 2 the rest. In plant 1, 85 out of 100 scooters are rated highly quality. In plant 2, only 65 out of 100 scooters are rated. Now we are going to choose a scooter at random. We are going to find the probability that the scooter came from plant 2. Solution to the problem. Let E1 and E2 be the events that the plant 1 and plant 2 manufacture scooters. Let H be the event of producing high quality scooters. Given P of E1 is equal to 80 by 100, which is equal to 0.80. P of E2 is equal to 1 minus P of E1, that is equal to 20 by 100, which is equal to 0.20. Next, P of H be the event of producing higher quality scooters from E1, which is equal to P of H given E1 is equal to 85 by 100, which is equal to 0.85. P of H be the event of producing higher quality scooters from E2. So P of H given E2 is equal to 65 by 100, which is equal to 0.65. Next, we have to find P of the scooter came from plant 2, that is equal to P of E2 given H by Bayes theorem. P of E2 given H is equal to P of E2 into P of H given E2 whole divided by P of E1 into P of H given E1 plus P of E2 into P of H given E2, which is equal to 0.20 into 0.65 whole divided by 0.80 into 0.85 plus 0.20 into 0.65, which is equal to 0.16049. Now we are going to see Bayes' theorem in statistics. We want to know how a change in interest rate would affect the value of a stock market index. All major stock market indexes have a plethora of historical data available. So, you should have no problem finding the outcome for these events with a little bit of research. For our example, we will use the data below to find out how a stock market index will react to a rise in interest rate. Here they have given stock price and interest rate, decline and increase rates, and unit of frequency. So in decline stock price frequency value equal to 1150, increases 850, total frequency we have 2000. Here the suitable tool is Bayes' theorem, as we have prior probabilities and we need to update it with new information. P of SI is equal to the probability of the stock index increasing. P of SD is equal to probability of the stock index decreasing. P of ID is equal to the probability of interest rate decreasing. P of II is equal to the probability of interest rate increasing. P of SD is equal to 1150 out of 2000. This is prior probability values. What we find after applying Bayes' theorem is posterior probability. P of SD given II is equal to 0.9499, which is equal to 95%. Thus, we can use the outcome of historical data to base our beliefs on, from which we can derive new updated probabilities. Now we are going to see Bayes' theorem in machine learning. Bayes' theorem is a powerful tool in the field of probability. Bayes' theorem is also widely used in the field of machine learning, including its use in a probability framework for fitting a model to a training data set, referred to as maximum a posterior or MAP for short, and in developing models for classification predictive modeling problems such as Bayes optimal classifier and Navy Bayes. Developing classifier models may be the most common application on Bayes' theorem in machine learning. Nevertheless, there are many other applications. Two important examples are optimization and causal models. Next, Bayes' theorem in artificial intelligence. It is used to calculate the next step of the robot when the already executed step is given. Bayes' theorem is helpful in weather forecasting. It can solve the Monte Hall problems. Next, Bayes in genetic prediction and testing. In genetics, Bayes' theorem can be used to calculate the probability of an individual having a specific genotype. Many people seek to approximate their chances of being affected by a genetic disease or their likelihood of being a carrier for a recessive gene of interest. A Bayesian analysis can be done based on family history of genetic testing in order to predict whether an individual will develop a disease or pass one on to their children. Genetic testing and prediction is a common practice among couples who plan to have children but are concerned that they may both be carriers for a disease, especially within communities with low genetic variance. Next, conclusion. As with any tool, Bayes' theorem also has to be used with caution. If there is authentic prior information, it can be used, but one needs to exercise caution if that is not the use. Thank you.